Greetings, my name is Jared Langevin. I am a research scientist at Berkeley National Laboratory. I'll be discussing an effort to quantify and communicate the potential benefits of building efficiency and operational flexibility for the U.S. electricity system. The intent of this effort was to provide a data-driven basis for federal energy policymaking around grid interactive buildings, but the framework is built up from the regional level, and we think it could be useful to states or utilities as well. This presentation addresses the learning objectives referenced in the program, which I invite you to read through separately. I'd also like to acknowledge this work as a collaboration between Berkeley Lab and the National Renewable Energy Laboratory, with the NREL side led by Chiake Harris. Thanks also to the U.S. Department of Energy for funding and managing this work, particularly Monica Newcomb, David Nemsow, and Karma Sawyer in the Building Technologies Office. And finally, thanks to the U.S. Energy Information Administration, or EIA's, Laura Martin for providing us with supporting data for this analysis. So historically, in federal energy policy assessments, building operations have been considered a static demand-side energy resource that can be communicated on an annual timescale across a broad geographic region or the U.S. as a whole. Increasingly, however, energy policymakers are interested in exploring buildings as a dynamic grid resource that varies across finer resolutions of time and space. What's driving this interest? Well, utility systems are being challenged by the need for greater energy generation capacity alongside the integration of variable energy supply sources such as wind and solar. And because buildings contribute 75% of U.S. electricity use, there is a clear opportunity to leverage energy efficient building operations alongside energy flexible building operations to more effectively utilize the renewable generation resource, making it more cost-effective to deploy, while also reducing periods of high stress on the U.S. electric grid. So our organizing question here was, how can we quantify this U.S. grid resource from buildings in a way that supports energy policy decision-making to drive the development of grid interactive efficient buildings? The framework we've been working on brings together several existing building energy simulation tools and data sets to enable transparent assessment and communication of the U.S. building-to-grid resource. We develop analysis capabilities for time and location-sensitive valuation of building energy use. We also define a core set of efficiency and flexibility measures, look at their interactions, and examine their impacts on electricity use according to a well-defined set of metrics. There are 4 stages of our approach to this. First, we establish the measure portfolios, so that's energy efficiency, or EE, demand flexibility, or DF, and a combination of those, which we call EE plus DF. Second, we apportion annual baseline case building energy use across all 8760 hours of the year, and that allows sub-annual assessment of technology impacts. Third, we assess the effects of our measures on those baseline hourly loads by developing unique operational profiles for each measure relative to baseline operation. And fourth, we scale up and evaluate the impacts of those building level measure operations to the electricity systems of various U.S. regions and across the country as a whole. As I mentioned, this analysis brings together a number of different simulation tools and data sets, each of which applies to various scales and regional boundaries with some geographical mapping that's required across scales. We start at the building scale, modeling baseline loads and measure impacts, simulated in a representative city for each of the 14 contiguous U.S. ASHRAE IECC climate zones. Here we use Energy Plus as our building level simulation engine. In the residential sector, we leverage the ResStock tool with Energy Plus as its engine for the simulations. And then in the commercial sector, we rely on the DOE Energy Plus commercial prototype models. We then turn to Scout, a software for modeling the impacts of energy efficiency and flexibility across large swaths of the U.S. building stock, to extend our expected changes in building level operations across a regional scale. And the 22 regions reflected in Scout's base case data are consistent with the EIA's Electricity Market Module, or EMM, analysis. Finally, when we communicate regional results, as you'll see in this presentation, we aggregate those 22 EMM regions into a more manageable set of 10 regions consistent with the U.S. Environmental Protection Agency's AVERT tool. And in turn, we can aggregate those further into the whole U.S. Let's look a bit more closely at our measure portfolios. There are three that we examined. As I mentioned, there's energy efficiency by itself, or EE. These are the conventional static efficiency measures that you're probably familiar with, corresponding in our analysis to the best available efficiency measures on the market in each year. Demand flexibility by itself, so that's DF. These measures modify baseline loads dynamically based on the time of day and associated grid needs. So they shed load during peak demand hours on the grid, they shift load to off-peak hours at the grid scale. And then we have a combined version of those measures, EE plus DF, where we look for these interactions. This table shows our residential measure set, again simulated using the ResStock tool, and we can focus a bit more on the flexibility measures, which I expect are somewhat less familiar to this audience. So first, we represent programmable communicating thermostats, PCTs, or also known as smart thermostats, that are able to schedule setbacks to thermostat set points during peak demand hours on the grid to reduce cooling in the building or heating loads as well. These thermostats also enable pre-cooling or preheating of a space in the hours just preceding the peak demand period. And we also explore measures like grid-responsive water heating, cycling, grid-responsive appliance, and electronic use, and we look to reschedule such operations from peak to off-peak hours. In the commercial sector, simulated using the DOE prototype buildings, we have the same measure organization, the same three portfolios. And here, again, focusing on the flexibility measures, we are looking at things like global temperature adjustment during peak periods. So that's setting up or down the thermostat temperature to remove heating or cooling energy use. We look at passive pre-cooling, which charges the thermal mass of the building in the hours preceding the peak demand period. For large commercial, we explore overnight charging of ice storage, which is then used to meet cooling demand during peak hours. And outside of the heating and cooling end uses, we represent continuous dimming of lights and low priority device switching to address plug loads. Just to note that all of our flexibility measures here adhere to comfort thresholds that we determined using ASHRAE and other standards. So I'd like to briefly emphasize the dimensions across which we evaluated these measure impacts. And a note here that each of these dimensions is simulated across multiple years in a time horizon that spans from 2015 to 2050. So keep projection year in mind as an overarching variable. A second note that we are looking at a technical potential adoption case here. So we're essentially taking adoption out of the analysis as a dimension. Any consumer or organization that can adopt one of these measures in a given year will do so. And that's assumed as kind of instant overnight adoption. So moving from left to right, we first look at the dimension of our scenarios. And I've outlined the three scenarios that we're looking at here, plus the baseline case. We model our measure application in multiple representative building types. We also model measure effects across a variety of residential and commercial energy end uses. And then each simulation case is run across the 14 representative cities, the locations designated by ASHRAE for its climate zones. And finally, we consider the unique utility system conditions that our measures should address for each location. So for example, when might we want to reduce loads, and when might we want to add loads in a way that's beneficial for the grid system in that particular location. So here's an example of our scenario impacts at the building level. We show baseline scenario operation as the dotted black line, as well as the operation of our three measure portfolio scenarios, in this case for the Atlanta location on a winter day at left and a summer day at right in residential buildings. The x-axis represents the hour of the day, and the y-axis represents the total electric load for the home in that hour. We also shade in system level conditions. The red shading represents 4-hour peak demand windows defined at the utility system level for this region, while the blue represents periods of low demand on the utility system. Looking relative to the baseline load patterns here, we can see that EE, energy efficiency measures, consistently reduce load across all hours. The demand flexibility, or DF, measures shed load from the peak period, so they remove that load, and in some cases build or add load during periods of low system demand. And then the combined EE plus DF measures represent, as you'd expect, a combination of these trends, deeper reductions on peak, but reductions across other hours as well. So how are these periods of peak and low utility system demand defined for each location? We use plots of the net utility system hourly load shape in a region, like the one shown here for the Southeast SRBC region, to determine daily periods of peak and low system demand for each of our simulated locations. So a net system load shape takes the total hourly electricity demand profile for a system, a day type, and a season, and subtracts out hourly renewable electricity supply for the same. The shapes we're plotting here are based on EIA, EMM data. Using those data, we normalize by maximum peak load and take the year 2050, which is the year with the highest degree of renewable penetration in EIA's data, as our reference. And we have one of these net system shapes for each month of the year and for 3 day types within each month, as shown in the plot. So taking a closer look at the example plot here, we see that net load tends to peak later in the evening across the seasons and day types. We define these peaks as seasonal 4-hour peak demand windows. Valleys or troughs in the net load vary across seasons. So in winter, the blue lines, for example, such periods occur in the early morning and midday hour ranges, while in summer, the red lines, a trough in demand occurs from the early to late morning hours. We define these periods where the hourly net load is close to the minimum hourly net load for that season as low net demand windows. And in general, our measures are looking to reduce or shed peak system loads, and where possible, move those loads to periods with low net demand, which overall lowers and flattens these net system load shapes. So lower, flatter net system load shapes are advantageous for a utility because they mitigate issues like fast ramps up in electricity generation requirements, curtailment of renewable resources, and the need for high electricity generation capacity during peak periods. So let's move on to take a look at some of our findings, and we'll start at the highest national level and move progressively down into more of the regional results and details. Throughout, we'll focus mostly on the projection year 2030 as a compromise between a near and long-term focus. We will also show 3 types of metrics represented in each plot here. So first, at left, we have the change in annual electricity consumption that is resultant of one of our scenario portfolios. Second, in the middle, we have the average change in hourly system demand during the peak period by season, summer and winter. Third, at right, we have the average change in hourly system demand during low net demand periods, again, by season, summer and winter. In each of these plots, all of the results above the thick horizontal black line represent increases in the given metric, while all results below that line represent decreases in the metric. And on the x-axis, we show each of the 3 measure portfolio scenarios, EE plus DF, DF, and EE. A few things to highlight in the national level plots. The deployment of efficiency measures, so that's the EE and EE plus DF scenarios, always yields substantial reductions in annual electricity consumption. So we see at left 723 and 744 terawatt hours are removed, or nearly 20% of the annual U.S. electricity consumption for 2030. Additionally, staying on the left-hand plot, the exclusive deployment of flexibility measures that shed load on peak and increase loads during off-peak hours yields basically no overall increase or decrease in annual consumption. So that's the DF scenario on this plot. Looking at our ability to shed load in peak hours, so we're getting to the middle plots here, we see the most potential when efficiency and flexibility measures are packaged together, the EE plus DF scenario, and in the summer season. So that yields a 182 gigawatt reduction And for reference, that's almost a quarter of the total US peak electricity load projected for 2030. On the other hand, moving to the right-hand plot, it's evident that efficiency measures counter our ability to add or build load during times of low net system demand. In both the EE and EE plus DF scenarios, the loads during these low net demand periods actually get lower, though when we package efficiency and flexibility measures together in the EE plus DF scenario, that mitigates this effect somewhat. Staying on this plot, when we exclusively deploy flexibility, that's the DF scenario, our ability to build load during low net system demand periods reaches just about 14 gigawatts. And we'll talk about how this reflects the nature of some of our measure assumptions, which we will get to in one of the subsequent slides here. We can break out impacts by influencing segments of the building sector. So looking at new and existing residential here and new and existing commercial. New in our definition is any building constructed after the beginning of the modeling time horizon, so 2015. And it's seen across all three metrics here that a majority of impact comes from the residential sector, particularly existing residential. So over half of the annual reductions and about 60% of average summer peak period reductions are from residential buildings. Over 80% of the average increase in demand during periods of low net demand on the utility system is from residential buildings. And during these low net demand hours, we do see more influence from efficiency measures in commercial buildings. This is because the commercial load is more coincident with these low net demand hours, which tend to occur towards the middle of the day or in the overnight or early morning hours. We can furthermore break out by energy use across all building types, and here we see some interesting differences across our metrics. Looking at cooling, for example, we see it's about 1/4 of annual savings for the scenarios with efficiency measures, but well over half of the savings of summer peak demand. And this reflects the high concentration of cooling loads and saving opportunities in those summer peak hours. On the other hand, plug loads yield the highest annual savings and strong winter peak savings alongside heating, but they yield relatively lower summer peak savings. And this is ultimately a flatter type of savings profile for those plug loads measures. Finally, examining the potential for load building during times of low net system demand on the right-hand plot, we see that in the flexibility only case, the DF case, water heating shows the most potential to build load in these off-peak hours. So why is this? For the residential water heating measure, we assume operation can be tailored more to the low net demand hours, and that includes shifting several hours off-peak if needed. By comparison, we restrict pre-cooling and preheating measures to the hours just before peak, to ensure their effectiveness in improving comfort on peak. For many regions, low net system demand does not occur in these pre-peak hours. It's only in places like California with high afternoon solar generation that pre-cooling and heating coincides beneficially with the valleys in the net utility system load chain. And just a note before moving on that results for individual measures within each of these end uses are also available in additional slides. And in those results, we see smart thermostats showing up prominently for load shedding, as well as water heating measures for load building. We also have result slides for later projection years when we see increased opportunity around the reduction of cooling and plug load end uses, both of which grow in the projected baseline. And glad to show those slides outside the context of this presentation. So these next set of plots get more into the regional results, focusing on regional summer and winter peak demand, which are shown via the blue bars at left and right, respectively. And they superimpose with the hatched white regions the regional peak demand savings that we found for our efficiency plus flexibility scenario. Looking at these blue bars, we see a lot of regional variation in the baseline peak demand, with the heavily populated Southeast and Mid-Atlantic regions, which also have a lot of electric heating, showing up most prominently. In terms of the peak savings from our measures, as a percentage of those baseline peak loads, these savings vary more widely across regions in the summer than in the winter. So the Mid-Atlantic, for example, shows a particularly high savings of 49%. This reflects more variable peak period definitions across our regions in the summer than in the winter. So in the case of the Mid-Atlantic and others like the Northeast, peak windows occur earlier in the afternoon, and that means that measures like thermostat setbacks will be more impactful given the higher cooling loads, not only in residential but in commercial as well, as the buildings are still occupied during these hours. Looking at the same plots now, but superimposing our load building potential as a percentage of the peak demand, and focusing on the scenario here with only flexibility measures. As previously discussed, we see generally low potential for load building across several off-peak hours, and we do see somewhat higher potential in some regions. So for example, in the Southeast and Texas in winter, on the right-hand plot, there is increased potential. In these regions, preheating before the evening peak period is more coincident with the defined periods of low net system demand than in other regions. So again, the timing of those low net demand period windows really matters to these results. So in the next few slides, we're going to return to the type of bar plots shown earlier, but with a focus on two of these regions, Texas and California, and some interesting differences in their outlook. Starting with California and breaking out measure impacts by building type, the primary thing to note is the stronger influence of commercial buildings than what we had seen on the national levels. So this is particularly evident for changes in annual demand and in the summer demand during both peak periods and periods of low net system demand. In the winter, residential does appear to drive changes somewhat more strongly. Moving to Texas now, we generally see more of what we saw in the national plots. So residential, particularly existing residential, more strongly drives reductions in annual and peak loads than in the California case. And we can glean more information about these regional differences by breaking out by end use. So in California, we see that plug load savings, which largely occur in commercial buildings, are driving annual reductions as well as, to a large degree, reductions in summer peak demand. Cooling reductions in the summer in California are also strongly driven by large commercial. But in this region, those peak reductions are about equaled by heating reductions in the winter, which largely occur in residential buildings. So in fact, heating reductions outweigh cooling reductions in our annual metric at left, as well as during the off-peak hours with low system demand at right. And this is in fact a region with much more of a mix of heating and cooling needs that are overall lower than other regions, as reflected in these results. Switching to Texas, by contrast, the prominence of cooling reductions in both annual and summer demand reductions is clear, and cooling even shows some potential for winter demand reductions in this region. This reflects the influence of residential electricity use in Texas. The high residential cooling load is also highly coincident with peak demand hours. The fact that we see a lot of cooling reductions even in the off-peak hours for this region shows that cooling is more of a pervasive need in Texas than it is in California. In the moderate California weather conditions, the cooling load appears to be much more concentrated around a handful of hours. So in the last two slides, I'd mainly like to drive home the point that all of what you've seen thus far is an aggregation of results data that are more granular both in space and time. This set of maps shows, for example, that our estimates of scenario impacts on annual and peak demand in a given year, here the year 2030, are resolved in terms of each of the 22 EIA electricity market module regions. And then to the point about temporal resolution, here we are showing hourly demand impacts in 2030 from one of our scenarios at the utility system level across different EMM regions, which are shown in the columns, for different seasons and day types, which are denoted by the different lines in each of the plots. In fact, these results are summarized from an even more granular set of estimates of scenario impacts on system load for all 8760 hours of the year in each of our regions. So these sorts of detailed regional time-resolved data may be useful, we think, to utility planners who want to represent potential changes on the demand side in supply-side modeling at an hourly resolution. To conclude, we view this analysis as an important initial foundation for quantifying the building-to-grid resource. The quantitative framework we've established is robust. It brings together a number of existing tools and data sets, and we think it can be easily updated as more relevant data come available. Our analysis overall revealed that there really is a strong potential importance of the building sector as a resource for the electric grid. And specifically, we show that in 2030, up to 182 gigawatts of net system peak load, or almost a quarter of total US peak load for that year, could be removed by efficiency and flexibility in buildings. We do reveal some complexity in the interaction between efficiency and flexibility. So while they're certainly complementary in removing peak loads, efficiency appears to also remove the opportunity for flexibility measures to build loads off peak, as is needed to flatten the shape of utility system loads net of renewables. Our framework also allows us to attribute modeled impacts on utility system loads to specific measures, end uses, and building types, which is essential in informing concrete policy approaches to this problem. And we find, for example, that cooling, particularly in existing residential buildings, has the strongest influence nationally on peak load reduction. We also see opportunities for efficiency and flexibility measures to address growing plug loads in commercial buildings, and these are influential both on and off peak. So I encourage you to look through the supporting documentation for the tools and data sets mentioned in this presentation. And with that, I say thank you so much for your attention, and I look forward to your questions.